This is going to involve a bit of a recap of the RAET components for that training, but for obvious reasons, a lot less. Because I've got, what, like 45 minutes instead of 4.5 hours. Okay. Now, who here has tried to run Salt with RAET? Okay. Then I'll start by explaining how to run Salt with RAET. It's really straightforward. Okay? All you've got to do is go into the master config and the minion configs and change an option, transport, to RAET. And restart the master, restart the minion. Okay? It's going to generate new keys. And so you will have to re-accept the minion keys for the minions because it uses elliptic curve key cryptography instead of RSA. The other thing that you've got to do, no, I got it, don't worry. You're calling me out. Colton knows that I screw up constantly though, so he's on the ball. You also need to install different dependencies, okay? So for normal Salt, for the transport layer, you've got ZeroMQ, PyZMQ, PyCrypto, M2Crypto. For Salt with Salt with RAET, you've got the RAET library, which is all Python. You've got libnacl, which are the Python bindings to libsodium, which is the cryptographic library. And you've got IOFlow, which is a pure Python library that we use for flow programming. Now, let me explain what these dependencies are and why they're there. So, what we're looking at here is that RAET, of course, is, RAET. It's a UDP and IPC protocol, fully asynchronous. Now, RAET, all of its cryptography comes from a library called libsodium. Who in here is familiar with libsodium? All right, an explanation is in order. Back in the 90s, back in the late 80s and early 90s, a type of cryptography was developed called elliptic curve cryptography. It's substantially higher performing than traditional RSA cryptography. Very, very flexible, very cool stuff. The problem that it had was the same problem that RSA had. It was heavily patent encumbered. And so nobody could use it for a long time. Now, Dan Bernstein, for those of you who don't know who Dan Bernstein is, he is the guy who wrote DGB, TinyDNS, and QMail. And he is a security researcher. And he has an incredibly good track record of writing very, very secure software. He's the guy that said that if anybody finds a legitimate security fault in DJB DNS, then he'd write him a check for $1,000. And he's only written one check, which for a DNS server is pretty freaking good. Okay? Dan Bernstein developed the algorithms for an elliptic curve cryptography that very carefully bypassed all of the patents so that it could be publicly used. This cryptographic library is called Curve25519. You've all got that? Okay, so that's the asymmetric encryption algorithm. It's called Curve25519. He also developed a stream cipher. So a stream cipher, a symmetric encryption algorithm, so you've got the same key on both sides. And that is called Salsa 20. And there's a variant called Cha-Cha 20, which you may have heard of, Cha-Cha-20. I guess he likes to dance. Cha-Cha-20 has been proposed as a replacement for AES by many people like Google for TLS. Okay? And so these algorithms are now in widespread use. They're used by default in OpenSSH. And if you're paying attention to OpenSSH, just as an example, they recently did announce that they no longer need to have OpenSSL installed to use OpenSSH, because they've built in these algorithms directly into OpenSSH. The other thing that Dan Bernstein did when he developed these algorithms, these encryption algorithms, is that they were developed in such a way that they're completely safe to use. When you build an encryption stack with OpenSSL, you have to be familiar with many things. Because you get your AES and you put your cyclic block cipher on top of it, and then there's lots of block ciphers to choose from. And cyclic, honestly, I'm not going into that. You got, et cetera, et cetera. There's layers, okay? And I'm not going to pretend to tell you all of them, because then a security researcher will file a security fault on me personally. They would do that. Okay. And so that's the end result. We've got a cryptography library which is extremely safe to use, substantially faster than anything else that is out there, and that was developed by somebody who has an extremely good track record. What Dan Bernstein does not have a good track record for is writing software that anybody wants to actually use or package. As, if you ever want to go and talk to the guys who maintain the Debian packages for DJB DNS, they're very upset. And so somebody other than Dan Bernstein wrote libsodium, which is the implementation of his algorithms, and it's very well maintained. Okay, I wrote libnacl, the Python bindings to that library, because the existing binaries were not portable enough. Okay? And so then those Python bindings to the C library of libsodium is how we get our encryption. So the keys that you see coming out of RAET are elliptic curve keys. So again, substantially faster cryptography. And the cryptographic handshake in RAET implements curve CP, which was a handshake developed by Dan Bernstein, and is very thoroughly vetted. You can go to curvecp.org and read all about it till you're blue in the face with all of your wonderful cryptography knowledge. Okay? So that is libsodium and libnacl. Libnacl is a perfectly viable standalone Python library that will allow you to do really cool encryption that is perfectly safe and incredibly easy to use, which we have had the bindings vetted by cryptographers as well. Okay? And so honestly, it's seriously the easiest crypto out there. It's really slick. Go check it out. We got docs up on Read the Docs. We have docs for that one. Okay. The last dependency is a thing called IO flow. Now, IO flow is kind of trippy. I'll use trippy. Because what IO flow is that it is a flow programming framework. Has anyone here ever heard of the flow programming paradigm? Like I've talked to all of you that have your hands up almost. And like there's like one other. I'm not going to go into the details of the flow programming paradigm, but RAET is built using the flow programming paradigm, and Salt's RAET daemons are built using the flow programming paradigm. And we've done it that way because it makes the code substantially more pluggable and portable, and very, very easy for us to manage. And it's a great programming paradigm, but this is not the talk for me to rant and rave. No, not the talk for me to rant and rave about flow programming, okay? Unless we've got like time at the end and they'll, you know how that goes. But we probably won't. Okay. So, the dependencies. And so now we are going to dabble in RAET. Let me give a quick overview of one. You can make fun of me because these slides have the wrong, that one. Okay. So before I dive into RAET, I want to go over a quick overview of how ZeroMQ provides asynchronous sockets, okay? To kind of help you understand those fundamental differences as to why ZeroMQ has been great for us, but also why we went through the trouble to develop a UDP protocol, which is a terribly difficult thing to do, that is reliable, et cetera, to get away from this model. And it's mostly because while ZeroMQ is fantastic, we did end up pushing it to its limit, as we run into on a very regular basis with our large deployments. And if you want to talk to somebody with a large deployment of Salt, this is the room. Now, I'm sure you can find them. Yeah, that guy right there, Thomas Jackson. Raise your hand. That man maintains something like a 70,000 server deployment. Okay? Now, ZeroMQ, what it does is that when you have connections come in, for all of the connections that come in, and it's not technically all of them, but most of them, et cetera, it creates lots of POSIX threads. So it creates many POSIX threads to track all of the connections. This is why your file descriptor count goes up really high when you're running a heavy Salt master, okay? And so all of those threads get abstracted into a single socket interface. And when I say a socket interface in this sense, I'm talking about a programmatic socket interface. You know, a socket object that you create and then you receive and send off of it. When you're working with ZeroMQ, all of these are TCP. And so it is an asynchronous system simulated on top of a synchronous system. And then with ZeroMQ, we've got all these different topologies that we can use. So we can use pub/sub, right, rep/rec, push/pull, all of these things with ZeroMQ. But the socket inherits the behavior of the topology that you give it. And that's why we have to have two TCP sockets open on the master, is because ZeroMQ won't allow us to do request-reply over the same socket that we do the publish out of. Okay? And so if we've got and so ZeroMQ has these unidirectional and bidirectional constructs. And so the other problem that we run into is that if we have a bidirectional construct in ZeroMQ, then a message comes in from one of these, we pop it off, or we'll do a receive. So we receive this message. I can't receive another message until I reply to that one, because the context of the socket is locked to the person, to the system sending the message out, okay? And so that's fundamentally how it does the bidirectional routing, which is, again, fine for a lot of situations. But we wanted to be able to batch these commands in a more fluid way, okay? And so that's ZeroMQ. Oh, also, on the slides, I do have movie quotes, if anyone can, figure out the movies that they're from. That's an old war movie, by the way. Now, how RAET works is different. One, RAET is UDP. Now, RAET's been built in such a way that we can build all of the cryptographic constructs on top of a TCP socket as well. And we have every intention to do so. We just haven't done it yet. You know how that goes. There's always something that you want to engineer. So, with RAET, RAET, by the way, stands for the Reliable Asynchronous Event Transport. We had to put reliable as the first thing because it's UDP and that's what everybody always asks. We built reliability into the protocol. Okay. How RAET works is that we've got one socket that can do everything, and all of the routing happens in software. Okay? So instead of having multiple TCP sockets on the OS, we're able to say that we're bound to one UDP socket. Okay? When a message comes in, that message itself needs to have routing information about where it came from and where it needs, so that we have an origin. That is built into the RAET protocol. When you pop a message off, it will tell you the authenticated origin of where it came, guaranteeing that what it says the authenticated origin is really is its origin. Okay? So the cryptography floats the authentication up to the application layer, which substantially, that solves all sorts of problems. I'm not going into it, but it's good. When it receives a message, instead of that message, I guess technically it's, appended. Instead of us binding the socket, it just pushes that message onto a queue. And so the benefit there is that what we do is evaluate an entire queue of messages at a time and then send replies out in batches. And so the end result is that we can do things in a much, much more asynchronous fashion because it ends up being queue and stack based. And so let me come back to this concept. When you build a socket normally in software development, you make a socket object, right? And you send and receive. And when you call send, it sends. And when you call receive, it physically receives the message off of the wire and onto the wire. With RAET, what you do is you take a queue and you append the messages that you want to send on the queue so that you've got n number of messages, okay? And then you tell them all to go at once. Now, again, the main benefits that we see doing this comes with true asynchronous operations. We don't end up having an operation tied to a specific instance of a request. And so what that means is that it makes it very, very easy for us to ingest n number of requests, prioritize them, deal with them according to how they need to be dealt with instead of just round-robining them, use concurrency models inside of our worker processes so that a worker can be concurrently working with multiple requests that are all waiting for different I/O blocking, okay? So that the worker is able to max the CPU better. The goal being that you won't have to run as many workers and still max your CPUs. The whole I/O blocking thing is why you generally want more workers than you have cores. Because most of the workers are I/O blocking most of the time to read a file or whatnot. They're reading all the pillar files in, they're contacting databases, et cetera, et cetera, et cetera. Okay? All right. So, another really nice thing about RAET, to come back on the encryption really quickly, is that one of the classic arguments with SALT had to do with the fact that SALT with ZeroMQ has application layer cryptography. And it's one of the biggest constraints that we run into from an application development perspective. And we, of course, I've explained many times that we built application layer cryptography because we were unable to accomplish the same performance and scaling metrics if we didn't. But so the nice thing about RAET is that we were able to create socket layer encryption. And so with RAET, we're able to get much more fine-grained encryption and encrypt things in a much more secure way, which is described better by the curve-CP document. Okay? And so then the nice thing about RAET, just standalone as a protocol, is that it has all of the cryptography built into the protocol. It also has in-band key exchange built into the protocol. And so the protocol itself is the thing that shoots the public key over the wire to say, are you willing to accept this public key? I am unfamiliar with another protocol that does this. Okay? And so we've worked very, 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 very hard on getting all of those pieces built in. All right. Any questions so far? Yes?
What if I don't want to accept that public key?
Well, then you reject it with SaltKey.
Oh. So there's a way in the protocol to say, yeah, I don't want to.
Yes. Yeah, so within the protocol, there's a class that you override and then pass your overrided object in to do whatever type of key management you want. And it's got a default class that's pretty straightforward. But of course, SaltKey overrides that. We've got a SaltKey backend class, overrides that class. And so when a key comes in, it's all still just SaltKey. One thing that I should really emphasize is that if you switch from ZeroMQ to RAET, all your operations are the same. SaltKey looks the same, the salt command's the same, et cetera, et cetera. It's all the same. Okay? Does that answer your question? Okay, yeah. How do we maintain the order of the messages? Okay. The RAET packet header contains ordering information. And so the protocol itself also does pre-segmentation of the messages to a configurable length so that it can be configured to pre-segment based on your network. So if you're running RAET inside of a jumbo packet network, you can go in and change those settings. I'm sorry, I do not remember that particular setting off the top of my head. And it's clearly not documented. I'll get that documented. Which will, of course, improve the performance. So, yeah. It's all in the header. Corey?
Yeah, from a networking perspective, does it transmit and listen on the same port? In other words, how much work am I going to have to do convincing my security guy that it does require oxygen and will in turn approve this?
Yes, RAET transmits and receives on the same port. So you need to open one UDP port bidirectionally.
What's it by default?
Sorry?
Is there a default?
What is it by default? I think it's 4510. Okay. That's documented. Be nice, Thomas. Yes, the minion itself does need an open port. Yes. One of the things that we're trying to do is build, like I was saying, a TCP layer directly inside of it so that we don't have that problem. Okay? All right, because again, the goal is that it doesn't matter what topology you want to deploy Salt in, we want to be able to do it. Yes? Okay. All of your attack vector explanations are taken care of in the curve-CP document because we implement their handshake and their encryption protocol. Okay? But all of the cryptography attacks are taken care of, and all of those exist entirely on that libsodium layer as well. Okay? Or I should say, they don't exist. All right. But yes, thank you. There's a number of attacks that are taken care of by the curve-CP system that are also ignored by other cryptographic systems. Dan Bernstein is nauseatingly thorough. Okay. Now, I started talking about this one a little bit, and it's the concept of a stack-based network interface. This is something that, a lot of people that I've talked to have a really hard time dealing with this. They want to receive and send so badly. But so this is something that's really, really important to remember about RAET. And it's also one of the biggest benefits. Because when we come back and we look at RAET as a protocol, the fact that it is stack-based means that it makes it really easy to build those topologies that you get with ZeroMQ on the fly. So instead of using somebody else's implementation of a pub sub, all you've got to do is fill a stack with all the messages to all the people you want to send them to and tell RAET to flush the stack. And that's a pub sub. Okay? All you've got to do for a request reply is make sure that routing information gets sent back and forth relative to the message. And that's another nice thing, is that you can start to build these message communications in a completely abstracted way. So that when you send one message out that says, hey, do X, that minion could send 18 messages that are unrelated to X before it sends its reply to that one message back, and then the software router is able to deal with those associations. And that also moves into why flow programming works really well with that model. Because flow programming allows us to just organize everything easily inside of a data bus as to where all of these bits of data are being routed. Okay? All right. So, stack-based. It's different. Sorry. Now, in RAET vernacular, we've got these things called roads and lanes. And so we've abstracted these names primarily because a road can be virtually any interhost communication, network or non. Okay? And so the only road stack that we have right now is UDP. Like I was saying, we want to build more road stacks and just plop them in underneath all of the cryptography code. Okay? But we've also got this concept of a lane stack. Now that's the idea of, or that's just in-a-process communication supported by RAET. And so when we come back, and look at this, the benefit, or rather just kind of how it works, is say we've got machine A and machine B. And then on machine A, we've got a process that has a RAET socket, machine B, process, RAET socket. And the machine A has another process, okay? And machine B has some more processes. So obviously they're using IPC to communicate in a process. So RAET abstracts in a process communication in the same way as a stack, and will automatically do platform detection and use mail slots on Windows and Unix domain sockets on a Unix-based system. Okay? Now the next thing that's nice about combining roads and lanes is how we're able to now route packets. It makes it very, very, very easy for us inside of Salt's router. So Salt RAET has a class that routes packets, looks at some extra routing information, which we put in the encrypted body of the packet. And then that routing information knows where to send those packets. So it makes it very easy for process. So we've got process 1, 2, and 3. It makes it very easy for process 3 to continually communicate with process 2, more or less as if they were local to each other. Okay? Because we're able to route between them continuously. And we can do it without maintaining a persistent connection or a persistent logical connection that's being managed through POSIX threads the way that routers and dealers work in 0MQ. All right. So I keep kind of walking over there as if I'm going to push the button. Wow, have I not beat this one into the ground already? I should move this slide. Happens every time. It's encrypted. Okay. Here's something that is documented. Now, so admittedly, I haven't linked this to the Read the Docs page yet. The Read the Docs page on RAET is still terrible. Have I apologized enough for my lousy documentation? So we've been working our tails off to get this thing production ready. I mean, and we've got just this long list of customers that are waiting for it, et cetera, et cetera. But don't worry, everything is very thoroughly documented, or will be. We're working on that. So, a warning before I dive into this tutorial. RAET is, from a user perspective, it's fairly raw. We built this thing ground up, not top down. And so that means the code I'm about to show you is kind of verbose to set up these stacks. And the main reason why I'm showing it to you is just to help you understand kind of, what RAET is and how it works. I'm not encouraging you to actually write code based on RAET quite yet. It's something that we built directly into Salt, works great, et cetera, et cetera. But it's got a ways to go before I'd say, hey, this is the next cool thing. Because usability is kind of lousy still. Okay? So you've been warned. Okay, we import RAET and we create something called the road stack. The default port for RAET is 7530. And by default, it'll just attach to all interfaces. Okay? RAET maintains a cache on the hard drive of its connections. The reason that it does this is so that when you shut down a RAET connection and bring it back up, it can reinitialize all of its historic connections transparently. If you don't want to keep that cache, then just make sure that you've got clear all dir before or after you're setting up those sockets. Okay? Now the next thing is that generally, when you're used to saying, I'm going to send to something, you'll give it a network address, right? With RAET, again, it maintains connection status. And so the stack object that we're creating here, this road stack alpha, needs to or will contain these remote estate objects which track all of the remote connections. Now, so in this example, we're setting up alpha and beta on different ports. We're going to make them talk. And then we add beta to alpha. Okay? Right here. And then we call the join command. The join command will do the cryptographic handshake. If we come back up here and look at, yeah, there we go. One of the options we put in here was auto. And RAET has 3 modes of key acceptance. We're being lazy here and just giving it the Salt equivalent to open mode, meaning we don't really care about authentication. This is an example. Okay? RAET in its current state does mandate encryption. All right. And so when we call that join, we call the join with the UID of the remote that we've added in. When we add the remote in, that HA is the address. That's a tuple, as you can see up above here, of the IP address and the port. That should be somewhat familiar. Okay. And let's see. Yeah, and then we can send messages back and forth by not calling send and receive, which is great. On the stack object, when you call service all, that says to all the ports, let's send anything on a send port, receive anything on a receive port, and put it in the stack for us to work with. Okay? Don't I have a transmit in this example? It's terrible. Absolutely terrible. All right. On the stack, we would say stack.transmit. I'm sure that there's a... What? I went past it? Yeah. So we're able to say alpha.transmit message and then the UID of the remote that we want to send it to. So again, I'm just showing you this because we're in a RAET class. I don't expect you to write a ton of RAET code. And yes, it feels cumbersome. We're working on that. The important bits is that the protocol works extremely well under the hood, even though it's a pain in the backside to program with still. All right. Does anybody have any questions? And I was going to say, if we've got, I'm actually going to do a quick introduction. This is terrible, finding my mouse. Yeah. We've got a time.sleep in the loop. I thought we were going real async. Come on, man, is what he's asking. All right. To answer that, I really need to go back to a flow-based programming paradigm. Okay? So, effectively, if we just keep checking, we are polling the socket when we're calling to receive. It is not blocking, waiting for new messages to come in when we call the socket receive. Okay? Again, this is a little different. And that's because absolutely nothing waits. And so when we are done processing messages, you sleep for a bit before you go and start grabbing more messages. Generally not for a whole second. Now, this is really where flow-based programming comes into play in a really big way, which is me going all the way back and, no, I went too far, I'm terrible. That one. Because the idea behind flow-based programming, which is a very, very important tenet to how RAET works and how Salt RAET works, and is also very, very, very close to how Salt itself works, before we got this in, which is why porting it over hasn't been too terribly difficult. But flow-based programming is the concept where you've got three things. You've got a scheduling state machine, a data bus, and black boxes. Flow-based programming allows you to create completely decoupled code. It only relies on the data that goes into the data bus, which means that it's very easy to replace individual components. It also means that it's very easy to morph the activity of your application in line because it's just going through and executing black boxes. Okay, what I'm saying right now probably doesn't make any sense because I'm totally skipping a ton of introductions. So, sorry. How the scheduling state machine works is that it evaluates, each black box is like a Python function that doesn't block, that it's intended to be CPU bound, okay? The scheduling state machine iterates over all of those functions and calls them based on the schedule that's passed into it. And then, when it does a complete iteration of all of its calls, it says to itself, how long do I sleep before I do another iteration? And it sleeps based on whatever time is left in the window. So if you tell it each iteration should take 1/100th of a second, and it takes 1,000th of a second, then it'll sleep the remaining 999, so it doesn't just peg your CPU. Because if we're doing truly asynchronous programming, and we never have anything that's waiting, then you're going to end up pegging your CPU. Yes? Why don't we use an event-driven mechanism to wake up after an arbitrary amount of time? There's absolutely nothing preventing us from building it that way. All you have to do is build a behavior that waits for the event inside of the flow system. Okay? All right. Yes, I completely agree, and we talked about this. We're going to make one that's better. Don't worry. I told you to be nice. Okay. To use flow-based programming, you need to have a flow-based programming framework or use a flow-based programming language. So since flow-based programming languages are terrible, ugly, and only used by the robotics community, we certainly don't want to, rewrite things to use those. And so we use a flow-based programming system or framework called IO flow. And so that's the last dependency with the RAET system that I want to talk about. And so, actually, how much time do I have? When's this end? 15? 2:15. All right. So I'm actually out of time, but I'll explain this really quickly. So we got our flow programming framework called IO flow out of the US Navy. It's a long and crazy story, but we convinced them to open source it. Okay? Thomas Jackson and I had a wonderful conversation yesterday about how we want to make one that's substantially better than what we got out of the Navy, primarily because now that we understand how it works, we can build one that isn't just suited to robotics and one that can be suited to highly dynamic asynchronous programming models. Okay? Hence why he's giving me crap. Okay? But so that is the IO flow dependency. All right. There is an open Q&A with me in this room after this talk. So this talk is done.